In this video, I will explain degree of freedom. So let's assume we have independent observations of x1 through xn and all xi for all I from 1 to n. They comes from normal distribution with mean mu and variance sigma square. Let's assume this. And from the observation, we can estimate mu value. So let's say this is mu hat from the empirical mean x1 plus x2 plus up to xn over n. That is empirical accuracy, right? And we can estimate sigma square as well. Let's say this is sigma hat square. We basically sum up from I1 to n. And from the definition, we can think xi minus mu hat square. And we should normalize this summation because we have to estimate sigma square. So we have to divide this summation by n, right? Because we have n number of observations. But when you check the expectation of sigma hat square, this is not sigma square. Indeed, we have to replace n by n minus 1 so that we can have expectation of sigma hat square is equal to sigma square. Okay, so you can easily check this property by replace this mu hat by this. Okay, so this is kind of homework, so you can check from yourself. But the point of this video is essentially n-1 is the degree of freedom for this estimation. Why the degree of freedom is n-1? Essentially, when you have x1 through xn-1, and if you know what is mu hat, basically you can directly understand or achieve the value xn. Why? Because we know mu hat is x1 plus x2 plus xn over n, and because we know the value from x1 through xn-1 and we know the value mu hat, we can naturally calculate the xn value from n times mu hat minus x1 plus x2 plus xn-1. So here, when you have the value from x1 through xn-1 and when you know the value mu hat, xn has no freedom. The value of xn just decides from the previous observations. Because of this property, we say the degree of freedom in this case is n-1 when you know mu hat. Of course, when you don't know mu hat, if there is no information on mu hat, the degree of freedom is n, right? Okay, so degree of freedom is n-1 means essentially among the random variable xi minus mu hat, and this one of random variable is usually this. So when you estimate sigma square, you just need to normalize with n-1. Okay, so this is a basic relation between degree of freedom and normalization constant when you obtain the sigma square. Right. Here is another example. Let's assume some linear model with multi-input predictors. So let's say yi comes from this linear model beta 0 plus beta 1 xi1 plus beta 2 xi2 plus beta p xip plus epsilon I. So there are p number of predictors, and at each time we observe a value yi with a independent random noise epsilon I. And let's assume the epsilon I comes from a normal distribution with mean 0 and variance sigma square, right? So again, from the linear regression algorithm, we can obtain the parameter beta 0 hat, beta 1 hat up to beta p hat from this optimization problem through beta 0 to beta p. I want to n yi minus beta 0 minus beta 1 x i1 minus beta p xip square. Okay, that is a linear regression training process, and from this process we can obtain some nice parameter beta 0 hat to beta p hat. And sometimes we want to understand or we want to estimate the sigma square, and to this end we usually compute this process. So sigma hat square can be obtained from 1 over something times summation I1 to n yi minus beta 0 hat minus beta 1 hat x I1 minus beta p hat x ip square. Okay, so that is a very natural approach, and if we don't care about the degree of freedom things, this is very natural to divide by n because we have n number of observations. But again, the running process to know beta 0 hat to beta p hat use p plus 1 degree of freedom. Essentially, when you have the knowledge on x1 through x n and y1 through y n minus p minus 1, we can naturally understand what is the value of y n minus p through y n, because the obtained parameter beta 0 hat through beta p hat can give you the remaining information exactly, right? So each parameter estimation use 1 degree of freedom. So when you compute the expectation of sigma hat square, so this will be much more difficult to obtain compared to the previous example, but still you can compute the sigma square hat, the expectation, and the value will be n minus p minus 1 sigma square. So rather than 1 minus n, it would be much better to use 1 over m minus p minus 1. Okay, so for the case linear regression with p number of input predictor, because there are p plus 1 number of parameters, usually the degree of freedom to understand sigma square will be n minus p minus 1. So you have to normalize by n minus p minus 1. Okay, right. Let's look at another example. So in the LDA example, we estimate sigma hat square from some equation 1 over something times summation from k1 to capital K I such that yi equal to small k xi minus mu hat k square. So here there are n number of data point, and nk denotes the number of data point belong to k cluster. Okay, so in this case, the number of parameters we trained is capital K, because we obtain mu hat 1, mu hat 2, up to mu hat capital K from the data point from x1 through xn according to their cluster index. We separate them, we discriminate them, and then compute the mu hat k for each cluster. So essentially, we train k different parameters, which means when you remove the one data point for each cluster then without the capital K number of data points, still we can recover the same value from the knowledge on mu hat 1 to mu hat capital K. So in that case, the degree of freedom will be n minus capital K, and you have to divide by n minus capital K rather than n. Okay, so basically when you take the expectation of this value, the expectation will be n minus capital K times sigma square. You can easily check this one. Okay, so in that case, you have to use n minus capital K to estimate sigma hat square, right? But in some case, you want to obtain rather than sigma square, the variance of entire data point, you want to obtain the sigma hat k or sigma hat k square, the variance for cluster k data point. In the case, naturally, this will be normalized by nk minus 1 times I yi belong to k, yi equal to small k xi minus mu hat k square, because in this case we only have one single parameters and we have we have nk data point, only one data point. So in that case, degree of freedom is nk minus 1. So 1 over nk minus 1 is the light coefficient, light constant in front of sum of squares. And then with this equation, we can obtain unbiased estimator for real sigma k square.